about function composition a little bit, and then I want to talk about two other concepts, lazy evaluation, and we'll put these together. So let's talk about function composition just a little bit. Let's look at it a little differently than what we've been looking at so far. Let's take a small problem and see how we would work through it. So let's say for a minute we are interested in performing this operation. So I don't have a collection at this point, but we will. So given a number, find the sum of the double of the even numbers starting with the given number, right? So I want you to think about this for a minute. Given a number, some number given to you, find the sum of the double of the even numbers, let's say let's say 1,000 even numbers starting with a given number. How about that, right? So let's say we're going to write this. And I'm going to say compute 1 for lack of better words, and let's say 33. I'm going to just start with that number, right? And I want 1,000 values. So I'm going to say public static int compute 1 starting, and I'm also going to define for our purpose static int max equals 1,000. So we're going to return a total of the sum of the total of the double of the even numbers, but 1,000 numbers. This is a very simple problem, right? But anybody who is excited to write that code? Not at all, right? You're like, please, please don't single me out, right? You're sitting there like, I don't want to be the one writing it. Why? Because it's very degrading to write this code, isn't it? Right? You first have to start by int count equal to 0. How does that feel? Right? And then you say int number equals starting. And then what do we do after that? Assuming we go, oh, total, of course. Int total, assuming that it will be int, total equal to 0. Then what do we do? While count is less than max. Make sense? And then what do we do here? Number plus plus. But before that, if number mod 2 is equal to 0, then what do we do? Count plus plus, result or total plus equal to number times 2. And what do we do now? And then return number. No, return total. With me? What do you think of that code? There are only two answers. You may say, that sucks. Or what most Java programmers say is, that's not that bad.
Hide it behind a class.
Yeah, hide it behind a class, right? It's not that bad. But it really is sad, isn't it? It is. Okay, let's try this again, shall we? Now, notice how low level this is. We had to say count to 0 and increment the count and then check if the count has not exceeded max. That is primitive obsession. That is imperative style, right? Let's see if we can do this a little differently. I'm going to go back to this code. Let's actually comment this out so we can compare this with this code and see how this is going to feel. So I'm going to say return, right? That's itself is powerful to me, right? We're starting with a return. This is what I want to return. What do I want to return? Into stream. Well, actually, stream.iterate, because after all, that's what we are doing. We are iterating. So let's say stream.stream. So I'm going to iterate. What do you want to iterate from? From starting. And what do you want to iterate on? Well, element plus 1. And then I'm going to say the next thing, filter, given an element mod 2 is equal to 0. That is filtering, isn't it? We are only picking even numbers. Then what do I want to do? A map. Given an element, double the value. But how many do you want? Limit max. Isn't that powerful? Limit 1,000. Not less than max. Not less than or equal to max. On Fridays it's less than equal to, other days it's less than. No off by one error, right? Limit max. It's like there's no argument about it. Then what? Dot reduce, start with the 0 integer and apply the sum operation on it and return that result. Right? So that is function composition right there, very expressive. However, If you sit down next to a business guy and you're trying to explain, given a collection, I only get even numbers, and then I double them, but I only give you 1,000. And the guy is like, this is boring. In the other job I had, we would spend all night eating pizza, trying to figure out what the code is doing. You mean this code is doing exactly what I want you to do? The code begins to read like the problem statement, right? I mean, the disadvantage is you go home on time, how boring life becomes, right? So that's the beauty here, is that you can just express it, and that is an example of function composition. So we compose by using these transformation operation. So we take the stream. Oh, there's one more thing we did here which is pretty sleek. Stream.iterate, what in the world is that? Well, that's a collection, all right, but that's a very special collection. It's an infinite collection. It has absolutely no bounds to it. You may say, wait a minute, if it has no bounds, where would you store it? I mean, that's what we have cloud for. No, just kidding. So the point really is that it's infinite, but it's very clever. It says, I'm infinite, I'll give you everything you ask, but I dare you, right? If you ask for infinity, you get infinity, but you wouldn't, right? So that's where the limit comes in. So the limit says, I can produce all this for you, but I want you to limit this first 1,000 values. And this is a very powerful concept. Almost every functional programming language supports this concept, right? So you can do this in Scala, Clojure, name it. So you can get infinite collections, and you can get infinite collections here too. Infinite collection is actually phenomenally powerful. The biggest challenge with infinite collection is trying to formulate a problem into an infinite collection. The first time you do this is nerve-wracking, right? Because you're in denial that this actually could happen. But then you run to the computer, you play with it, make something work, and it works, and you're like, this is awesome. I'm actually working with the infinite collection. So it's really, really compelling once you get a hang for it. But I'm going to show you here the function composition aspect of it, where we are composing all these operations. So you take your problem and you transfer it to a series of composition. Please, yes, please.
Before you get too far away from infinite
Yep.
collections, will Java process the size of them?
Not ahead of time though. It literally does it on demand because it doesn't know how much you're going to ask for.
But if I just gave it that without max and asked it for the size, would
It,
it tell me?
so it's very clever.
Yeah.
It says, I'll give you a thing which will work later on. That's where the laziness comes in. That's where the smartness is, and we're going to see that in another example in a minute. I'll drill it down to a much simpler example than this to actually see that more evidently. So I'll come back to that. But what I'm going to show you in the next example literally is what's happening here too. But it's just easier to see in the next example. Another question or comment here?
No, I was just commenting that it's beautiful memory footprint.
Yeah.
The way it's handling.
Oh, yeah, absolutely. Yeah, it doesn't really expand. So let's spend a minute on that. Think of a stream as an abstraction. Think of a list or a set or a map as a concrete collection, right? So it's kind of like, I travel a lot, so I always try to use a travel example. If I fly from San Diego to Singapore, well, maybe I'll take about 14 hours to do that. Awesome. But if I make 3 stops in between, that's expensive. Because every stop punishes me with an hour to land, an hour to take off, and 3 hours on the ground. So to me, it's better to be on the air as much as I can than touch down and take off. Same concept here. When you are in a concrete collection, you're expending effort. The minute you zoom up to a stream, you're on the freeway or up in the air, right? So you're not really doing any computation or expenses until you nail it down to concrete type. So one of the key design concepts in Java 8 is you take your collection, zoom it to a stream, and keep it as a stream. So you start formulating your libraries with streams rather than collections. So what happens then is, I give him a stream, he gives you a stream, you give her a stream. We haven't expended any effort until he says, all right, now that I have all of this, I want to put it concrete. He expends the effort, but nothing in between. So that's where the real power is. So thanks for that question. So that's where the real optimization comes in terms of efficiency, and it's baked in already without us doing any work. And we'll see that in the next example as well. So that brings us to the next point, how this is going to be powerful. So let's look at one other example here. Let's say we want to take a collection this time, but we're going to do a certain operation with a collection. Let's say we have a list of integer, we'll call it values equals arrays.asList, But notice this time 1, 2, 3, 5, 4, 6, 7, 8, 9, and 10. Notice the sequence difference. So I got a 3 and a 5 and a 4 intentionally. So the problem is find the double of the first even number in the list. How do we do that? Find the double of the first even number in the list. Well, result equal to 0, output the result, but this time for int element in the list values. And what should we do here? If element is greater than 3 and element mod 2 is equal to 0, then result is equal to element times 2 and a break, right? So very familiar code, and you can see that it produces that result. Does it work? You may say, yeah, it does, because it produced the result 8. But you know what happens with code like this? About 3 months goes by, you hear a knock on the door, and guess who walks in? The tester. And what does the tester say? The tester says, your code sucks. And you say, I know it. But tell me how it sucks. That's what I don't know, right? That's what we don't know always. The question is, how does it suck today? Well, this code actually sucks and we don't know how it sucks. Well, we'll find out but by writing it in a functional style. So let's see how we're going to do this a little differently. Output. So what do I do here? Well, values.stream. I'm going to say filter, given an element, give me an element which is greater than 3. Filter again, given an element, give me an element which is even. And then I want to say map, given an element times 2. And finally, find first and get the value for me. So that's basically a functional style to get the value out. Now you say, well, they both produce the result. What's different? Well, the first difference is, let's not ask for the get. Let's just say find first and see what it does. Notice in this particular case, it's very smart. It gave us an optional 8. And I'm sure immediately you said, of course. Now you know why the tester walked in. Because the tester tried this with an empty list, or a list with no elements which is even. And then they tried with the element where there are even elements but nothing greater than 3. And they failed in so many ways, and they said, your code sucks in these different ways. Well, that is the sign of imperative code. Imperative code is a code that hides to hurt you when you least expect it. A functional declarative code is very open, very transparent. It tells you, reveals and says, hey, it's optional. I may not even have a result for you. And you're very defensive about it already, right? So you program very defensively. That's a good news, first of all. But I've asked for the result from it. It forces me. I can get the value in different ways. That's great. But if I showed you these two code, and if I try to tell you that this code in the bottom is awesome, and we can agree that it's awesome, right? Because it's more expressive, easier to write. The other code is kind of tangled up. You're in the for loop, you're going through, but it stacks up nicely. But there's always this one question we always ask. This is really nice, but what's the cost? If I tell you this is going to cost you 4 times more than the other code, you're going to say, not really, right? Well, but what if it doesn't cost you 4 times more? Well, how much can I pay for it in terms of computation? Let's come back to that. Before we answer that question, let's refactor this just a little bit so it's easier to answer this question. So sample is greater than 3. Let's change this to sample over here. Let's open this. So this one is going to be a sample, and in this case I'm going to say, even. Let's call it even. So sample is even. And one more, let's call this as sample, and then let's say this is going to be double it. So I'm going to write 3 functions here. So static, let's call it Boolean, is greater than 3, which takes a number, and it's going to simply say in here, return number greater than 3, and 2 more functions to serve that purpose. So this is going to be is even, and I'm going to simply say mod 2, and finally I'm going to say this is going to be double it. Let's make that int, and that's going to be times 2. So same result as before, because all we are using is the sample class in here. So sample double up.
You didn't change the method name.
Oh, of course, thank you. So change this to double it. So the result should be exactly the same as before. In fact, we could get back to this and say, what's the price of this call? Let's think through that. We got these values 1 to 10. So let's find out. So first of all, we got 1. Is 1 greater than 3? No. Well, this is a short circuit, we know. So it's not going to go any further. So is 2 greater than 3? No. Is 3 greater than 3? No. Is 5 greater than 3? Yes. Is 5 even? No. Is 4 greater than 3? Yes. Is 4 even? Yes. Double 4 and bail out. So that was 8 computations, right? So keep that in mind, 8. So get rid of that. Let's get back to this code right here. We take all the values in the collection. We check if every one of them is greater than 3. How many operations is that? 0. 10. Right? Is every number is greater than 3, that would be 10 if we kind of look at it naively, right? It cannot be 0 for sure, but that's 10 operations. Well, wait a minute, that's 10. It's dead on arrival, right? Because that one finished in 8 operations, here you need 10. But let's continue. That's 10. You're going to check if it's even. That's 7 more, so 7 plus 10, 17. Plus you're going to check if double the values, only which are even. That's 4 more. 17 plus 4 is 21. Oh boy. 21 operations compared to 7. Seems excessive, isn't it? Except for one small detail. Streams share a property that I've only seen among my children. They both are lazy to the bone. They don't do any real work at all, right? So you go to the stream and say, stream, filter, done. Filter again, done. Map, done. Find first, oh dear. We got to do some work now. And what do? They do absolute minimum to get through this. So in other words, look at this a little differently. Don't look at this as a collection going from one line to another. Instead, look at it as a single element being dropped down, and you see how far it goes. So you take a 1 and you drop it down. 1 bounces right here. Comes out this way, right? Because 1 is not greater than 3. Say so is the fate for 2 and 3, and 5 goes 1 level below and bounces out of here. 4 on the other hand comes down, comes down, comes down. Find first is, hey, I'm good with it. And the guys are like, let's wrap up and go home. Hey, what about these other values? Don't worry about it. No need to do it. In fact, let's go ahead and see if this is true here. So how many operations would that be? Exactly the same as the other one. No more, no less. Let's see if that's true. So if I go back to this code and I say output is greater than 3 for number, and let's also say the same thing here, output, and we say is even for, let's say in this case, number. Excuse me. And finally, let's go ahead and output, double it for, and then number. So when you run this code, notice that in this particular case, you did exactly 8 operations again, right? You check for 1, 2, 3, 5. Hey, 5 is good. Is even? Yes. Oh, but wait a minute, it's not even. Well, 4 greater than 3 is even. Double it. 8. We are done. It never ever looked at the other values in the list. Now here's the beauty of this. If you go a step back, and this comes back to your earlier question, look at this particular find first. So in case of Java, there are 2 kinds of methods in streams. These guys are called intermediate operations, and this is called a terminal operation. Operations like find first, reduce, all of these are terminals. These are the ones that convert to concrete type. The other ones keep you afloat in your stream. In fact, here's a way to think about this. Notice in this example, when I run this, let me do one more thing. I'm going to output here, just for us to see, done. And I'm going to remove this output from here for a minute. So if I go back to this code here and do this operation, you can see that all that output and the word done in the back, right? In the bar. But if I remove this part for a minute, now what happens? You can relate to this very easily because this happens at work. You know this colleague of yours, right? Comes to work in the morning, stretches hands and says, hey, where's the boss? Oh, the boss is on vacation today. Yes. No need to do any work, right? So notice, no work got expended. Done. And all that just, poof, it's as if he never came to work that day, right? So it's what happened? Well, that's laziness. Oh, by the way, you don't say the word lazy like that. You pronounce it very differently in Java 8. It's called efficient, right? So that is basically what you got here. It's very efficient in terms of it says, I don't need to be doing this stuff. So you get efficiency not by doing things faster. You get efficiency by not doing stuff in the first place that you shouldn't be doing, right? And that is the beauty of the efficiency that's baked into this library, so it can be very powerful. And now you see why the lazy collection, infinite collection worked. Because only on demand it works. And the minute you say, I'm cool, I don't want any more, he's like, cool, I don't have to do any more work. So you can start leveraging these lazy collections very effectively. So we looked at all of these. Let's put that all together with one final example here to see how we could use this. So let's change the example just a little bit and do something a little differently here. And I'm going to make sure I've got connected to the internet, assuming my box works here. Yep, that seems to be working fine. Well, I hope so, but it's not. Let's connect. So I want to make sure, so let's define a problem I want to work with. So the problem I want to work with is, given a list of stock symbols, I want to be able to find out the highest stock, great. So here is a bunch of stock symbols I have. Tickers dot, let's call it as symbols. So I got all these symbols with me, and I want to find out the highest stock price, which is less than $500, right? So let's do this in the traditional style first of all. So timeIt.code, so I'm using the functional style here to measure the time, and I'm going to say find imperative, and I'm going to say tickers.symbols is what I'm going to pass to this function, right? So that's my first call. Great. So now that I'm calling this function, let's go ahead and implement this. So this is going to be a find imperative. It takes a list of string of symbols, and I'm not doing any work at all. That shouldn't take a whole lot of time. Yeah, that's about close to 0. That's great. Now what do? I want to say list of stock info. Well, let's see what stock info is. Stock info is a little pojo. I've got a ticker, I've got a price, which are final fields, public. The constructor simply initializes them. They are final, they cannot change. And the toString simply prints them out. That's all I have in a stock info, right? So stock info, stocks equals, let's say new array list, the imperative style. And so I've got this empty array list created to begin with. Now I'm going to say for string symbol in symbols. And what should I do here? Well, stocks.add. And I'm going to say stock util dot, let's call it get price for the ticker symbol. So let's look at stock util. And the stock util says get price will go out to Yahoo Finance. Given the ticker, it'll get you the price for it, whatever the current market price is. And I'm not going to show you the Yahoo Finance, but you can download the code and take a look at it. But that's what this guy is doing. Great. I've got all the stock prices with me now. What's my next step? Well, my next step is list stock info. We'll call it stocks less than 500 equals new array list. And what do I do with this guy? Well, for stock info, stock in stocks. And this time I'm going to say if stock util dot is price less than 500 dot test, and I'm going to ask him for the stock. If that is true, stocks less than 500 dot add the stock. So let's again see what is less than 500 does. Well, this is a bit of a special function. Is less than takes a price. Notice it returns a functional interface. So it's a higher order function that doesn't take a function but returns a function. This is like give somebody a fish versus teach them fishing kind of a function, right? It says, I won't give you a result, but I'll give you a function that you can take home and keep calling it to get results, right? So that's a function, it's returning the predicate. All right, last step here. We got all the prices now. Let's do one more thing here. So let's say static, we'll call it stock info. We'll call it dummy equals new stock info with no name and 0.0 as the price. So that gets us fairly close to what we want to do here. The last step. So what do I do here? I'm going to say stock info high priced equals dummy to begin with for stock info in stocks less than 500. And I'm going to say high priced excuse me, equals to, this is going to be stock util dot pick high from the stock and the high priced. Once again, let's look at what pick high does. Takes two stock info, returns the one with the greater price. That's all it does, right? And the last step here, output high priced. So let's run this, and while it's running, let's talk about what we just did. We wrote 3 loops. Of course, we would never do that when we write imperative code, but we did 3 loops. But each loop took a separate responsibility, right? The first loop said, given all these symbols, I'll give you all the prices. The second loop said, given all these prices, I'll give you the ones which are less than 500. And the last loop said, given all these prices less than 500, I'll give you the topmost stock. And that was Amazon in all the lists we had. About 27 seconds, keep that in mind, 27 seconds, give or take. $375.43. Now, how can we make this better? Well, one way we can make this better is to merge all the 3 loops into one loop. That code will be concise, if we want to call it concise. Well, but everything will happen in one loop. That will be a little hard to understand, but that shouldn't be a problem, because we only write code, we never read it. So, that's one way to solve the problem, right? Or we could make this declarative, shall we? So let's try to make it declarative and see how that's going to feel. So let's write this one more time. So time it, code, and this time around, I'm going to say find, let's call it find functional, and tickers dot symbols dot stream. How about that? So let's bring in the stream here, and let's write the function. Shouldn't be hard at all. So public, here is our find functional, and this is going to take a stream of string symbols, and I'm going to say output, and symbols dot, help me out here, given all the symbols, I want all their prices. What's that? A map. So map stock util get price. Make sense? Well, now that we have all the prices, I only want to cherry pick some prices. A filter. So filter stock util is price less than 500. Well, here's a last clue. Salt is to pepper as map is to reduce. Hey, I like this game. Reduce, right? Reduce. And what is this going to take? Dummy and stock util pick high, and that gives us the price. I'm going to comment out this part. We don't have to expend the effort again for that. It was how many seconds, I remember?
27.
Thank you, 27 seconds. Let's run this. This is functional style, declarative in nature. So given all the sticker symbols, go get all the prices, check if they are less than 500, and among those, pick me the highest price, right? So, lot less code, isn't it? Very highly expressive code, easy to read, easy to write, easy to understand, and about the same time. Fair enough? So, wireless network connection, 1 second, not a big deal. Sorry, just because you write functional code, you don't get a better stock price. Same stock price still. But let's revisit what we just did. Imagine we don't have this bottom code. Imagine you had the top code. And maybe even you merged into one loop. And you know how projects go, right? Everything seems to be fine. People come to work, they actually smile at each other. And about 4 months goes by, you're about a month before production, and what happens? That tester again walks in and says, I got a problem. I said, what's your problem now? Well, the code is very slow. What do you mean it's slow? Well, I tried with 200 values, and it's taking forever to run. Now everybody is focused on making this code faster. And everybody is trying, what can we do, what can we do? And one guy has a brilliant idea. And he says, what if? And you're like, oh, no. Because the idea given to you was, how about using multi-core and multi-threads? And immediately your mind races back to the previous job you had. Remember the job you had? Where the code was sequential, everything was working fine, and one day they decided to use multi-threading, and suddenly what happened? The code turned into a monster. It did not look like anything you were working with anymore, right? And every night, you had to be at work, fix the bug. And while you were struggling with this code, you applied for the other job. That's called concurrency, right? And you're like, no, thank you. I don't want to do that anymore, right? That kind of concurrency we don't want. Well, what if the code structure doesn't change? I call this the master switch. I call it a master switch because it's as if you stand here and flip the master switch, and you don't change the code structure. So you're saying, hey, you know what? This is all cool, but I want to run this really faster. So all you did was change it to a parallel stream compared to a stream that you had a minute ago, right? That's what you're doing. And that's not what I expected the result to be. Okay. So, did I say it right? Parallel stream. And so all you did was you're converting this to a parallel stream. I got to see why it failed, if it does fail. So the point really is that you are asking it to convert to a parallel stream, and guess what happened? It's exactly the same price, no doubt about it, but a lot less time. But I did not change the code structure, right? So it's exactly what we saw before. What's the difference? Well, the map is no longer sequential, the map is concurrent. The filter is no longer sequential, it's concurrent. How so? Because we told what to do, we didn't tell how to do it. Hey, what happens if you don't say how to do it? It's easy to change what you don't say, right? If you give instructions to every single thing, then you got to change that instruction. Recently, I was working with a contract for a client. We had to change this contract 4 times within 24 hours because they want to tell every single thing in the contract. At some point, I tried to tell them, why don't you just say, write the contract as Venkat will do work? We can figure out the details later, right? So it's like, no, we got to spell out every single detail. Well, within about 2 hours, we were like, we don't want to do that anymore. We want to do something else. What do? Go write another contract. Finally, I got around to saying, you know what? We'll just change things afterwards. Let's just sign this. We won't talk until we sign. How about that? Works for me, right? So the point is that, right? We cannot nail the details. If we don't nail the details, it's easy to change. This is called seeding control. And seeding control is a good thing. Because the more you control, the more you lose. The less you control, the more you gain. And because you didn't say how to do it, but you only said what you want, the code underneath can decide how to do it, and you can flip this master switch at the top. Now, of course, the question here is, why a master switch? Why can't they do this concurrently all the time? Well, I got an email a couple of days ago from a gentleman asking, hey, if this is the case, why can't they do this like this all the time? Well, it's like mom says, go to the neighbor and get some sugar. And you got 2 boys in the house. One gets in the car and starts the car. The other one just runs barefoot. Who's going to be faster? Well, the kid with the barefoot, obviously. Why? Because it takes more effort to take the car to the neighbor's house, which is like next door. Whereas if you want to go to a grocery store, which is 5 miles away, the kid with the car outwins the guy with the no slippers, right? So you know what the problem is, and that's why you have the master switch. If the problem size is so small, if the task is quick, then you say, you know what? The overhead of creating threads is way too much. I'm going to do it sequentially, flip back, do it in the stream. Oh, the problem size is big. The data size is big. The computation time is big. Oh, the delay is big. Okay, flip the switch. I want concurrency, and you get to flip it. You can flip this at runtime based on these parameters, you can go through a loop and or a condition statement and say, now it's sequential versus, or you can go through a factory, whatever that you want to implement, right? But at the end of the day, you're passing the stream. The other code doesn't know whether it's going to run sequential or concurrent ahead of time. It can decide on the fly. And you get to decide it before you send it, and that's extremely powerful. Of course, it's not going to solve all your concurrency problems for sure, but it gives you a fairly good control over a very narrow set of problems, right? So use it for what it is worth, and for other things, of course, we still have languages like Scala, Akka, and tools like that, which we can rely on for real major concurrency problems, but you don't have to run to those solutions for simple concurrencies. So, but this doesn't come for free though. It comes because we did something really good, which is we were declarative, we followed the hygiene of functional programming, we didn't mutate global shared state, we kept our hands clean, and we used the transformation operations, and we worked within the constraints of what it provides for us. But not only are we writing a lot less code, the code is more expressive, but the performance comes back in surprising ways. In fact, I want to emphasize this. When I was writing a book on Java 8, I used a class, and my editors really asked me, really want to use this? And I had a good ticket to use. I said, I live in Colorado. She said, okay, you're allowed to do this. So my statement was this: lambda expression is the gateway drug. Streams are the real addiction. And this is what I get hooked on with. I was not happy with Java 8. I was like, I don't care about it. So I was kind of playing with it. I was like, is this really interesting? Why should I care? And I remember clearly that day, I touched on streams, and I stopped everything else, and I said, I gotta write a book on this. Because that's how compelling it was. And to me, lambdas were marginally interesting, but I've used lambdas in other languages, right? But streams, even though they're in other languages, the power of how quietly this becomes lazy and can give you this parallelization with it is purely amazing in my opinion. So that's what was the most exciting part for me, is to be able to use that functional style and then bring it into a parallel stream and use it. So, like I mentioned earlier, the biggest change in Java 8 is in the minds of the programmers. It's going to take us a lot of effort to rethink the way we do it. Not because it's hard, it is because it's different. And hard things are easy for us, but different things are the hard things for us. Because the evil in us is the comfort zone we have created around us, right? We think a certain way, and to rethink in a different way takes a lot more effort. The design patterns that you're used to programming with object-oriented programming, you're going to rethink the way you're going to use the design patterns. Where you were sending in anonymous inner classes with single method interfaces, now you can send lambda expressions. Where you were creating lazy objects using complicated factories, now you can use lambda expressions and lazy evaluations to do it. So once we start experimenting with these things, the patterns begin to evolve very differently, and the patterns are not as much as a burden as we used to. To me, one of the big signs of design patterns is the more pattern is a reflection of the weakness of a language. A more powerful language will require fewer patterns from you. With lambda expressions, those patterns become the way of programming, and we don't really call them as patterns. For example, in the example we saw where we were doing the total of even, total of odd, we didn't spend our time talking about that and saying, oh, look, this is a strategy pattern, but essentially it's a strategy pattern, right? We just don't celebrate these patterns because that's like the way of life. It's like Q-tips. You don't go around and say, look, I got to use Q-tips today, right? It's a normal, commonplace. We don't get excited about it. And to me, a more powerful language becomes, the patterns become a commonplace. And to me, that's pretty exciting because then we begin to use a very good set of tools. I was listening to somebody today and they said, well, I've never had a reason to pass functions around. And that's one of the problems, is because the language didn't give us the tool. We have been passing function around without knowing we are passing function around. Because every time we pass an anonymous inner class, we've been telling the function, you can't go alone, sweetie, stay with me here, right? And we don't have to do that. It becomes a lot more powerful, a lot more easier. And to me, that's pretty exciting. I hope you found that useful. Thank you.
Questions?
Yes,
please.
Quick question. So as you were coding there, I noticed that
you're hitting tab a lot or doing the tab yourself. Do you have the formatters already to handle sort of the separating everything and lining up the dots?
Right, so I've quit using IDEs these days. This is purely a text editor, but IDEs do that. In fact, IntelliJ IDEA does the vertical formatting for you already.
Okay.
Yep. So if you're into the IDEA, if you use this is mental muscle, Control Alt L, if I'm not mistaken. It's funny that you can actually use the shortcut, but you cannot say what it is. But it's one of those shortcuts where you press a L, and it will do the vertical alignment for you automatically, for example.
Yeah, we force preferences on everyone to auto-save and format.
Cool.
Save, so.
Awesome. That worked then. So Java 8 convention is the vertical alignment. That they decided halfway after I finished writing the book, so you can imagine it was a painful experience changing all that code, but it's still worth it, I think. So absolutely, so that alignment is important. Yeah. And also in good IDEs, they can give you clues as to transform functions from imperative style to functional style. And wicked cool, I was looking at one code and I told myself I cannot convert that from a lambda to a method reference, but IntelliJ IDEA said, no, I can't. And I'm like, I dare you, and it did. So this is where the IDE is smarter than the programmer sometimes. And then I'm like, darn it, how did you do that? And it actually walked up a few levels in the hierarchy and applied a base function instead of a derived function, and I could never look through that far, but the tool was able to do it. So I thought that was pretty awesome. Yeah, please.
I noticed that all your functions, you implement them as static method. Is that the same thing?
No, not at all. In these examples, I didn't use an instance, but absolutely. Lambdas can be either static or instance methods, or method references can be instance or static methods, either way. It will roll it out automatically as instance if you use an instance state. If you don't use an instance state, it will roll it as a static method under the hood. So it's smart enough to decide that as well.
Even constructors.
Yeah, even absolutely. So you can even say this : and pass a constructor around as well. So it's pretty smart. Yeah, absolutely. Please.
Yeah, in the case of the anonymous classes,
Yes,
I noticed that you didn't, there was no mention of a method. I mean, if that class had multiple abstract
Yes.
methods,
So functional interfaces are allowed to have at most one abstract method. So in Java 8, interfaces can have default methods, interfaces can have static methods, but functional interfaces can have all those, but only one abstract method. So your runnable, callable, action listener, file filter, any interface you have seen ever which has only one method, automatically those are functional interfaces. But if you look at interfaces like mouse listener app, you can use that because mouse listener has what, 4 or 5 functions. So that's not a functional interface. So only things, and the reason for that is you're passing an anonymous function, so it cannot do overloading. It cannot decide which one to call based on the signature. That becomes very ambiguous and hard to manage. So that's why these have to be. In a true functional language, you don't have interfaces. You really have these floating functions. Like if I were to write this in Scala, for example, just as an example, right? Not that Scala is truly functional in that regard, but in a sense, you would be defining some defined foo, and you would say my function fn, and then you would literally say input type map to output type. So this is the way you define a function in Scala as an example. So in this case, you notice we don't bind this to an interface. You're basically binding to a signature, right? You're saying this is my input type. It could be a tuple. You could have multiple parameters. Same way here, it could be a tuple. But you're not binding to an interface. The reason why Java uses an interface is the backward compatibility story, right? Because they want to be able to pass lambdas to threads and executor services, everything that's been around so far. So they tie your lambdas to functional interfaces to get that backward compatibility. If they didn't have that baggage to carry, that's why I was saying you're doomed either way, right? If they didn't have that baggage to carry, they could have had function objects, but Java doesn't have function objects. Scala does, and other languages do, and that's the reason for that. So we are limited to one single function interface, but that's not really a limitation because in other languages also you don't have interfaces to carry. Because we bring in an interface, that question even arises. Whereas in other languages, that question doesn't even arise because it's just a function we are passing. Good question.
Anyone else? All right, last call on the raffle.